Hello and welcome to this video. Today we'll be looking at CSEC physics. As you can see, we're doing thermal measurements. So this is just some questions from past papers on said topic. We'll just be going through and solving the questions and giving explanations and some tips as per usual. Alright, let's get started then with January 2011. So it says, in an experiment to identify, or rather determine the specific latent heat of ice, the following results were obtained. So we start with our initial mass of water of 30 degrees Celsius, which is 100 grams, and a final mass of water, which is where they added the melted ice at 20 degrees Celsius of 110 grams. And then they're giving us some assumptions down here. So these assumptions basically mean that we just have to assume that the water and the ice are the only two bodies transferring energy in this scenario, right? Because they said negligible heat capacity for the container, and heat loss to surroundings is equal to heat gain from surroundings, so there's no net heat change. Okay. So the first thing to do is to determine the mass of the melted ice. So I'm just going to put M, that's going to be Mi, which stands for mass of ice, is of course going to be the final mass of the water, which they gave us, minus the initial mass of the water. Which is of course 10 grams. Or if you want to convert it, that is 0.01 kilograms. Let's just write that because kilograms is indeed the SI unit of mass, and it's always good to have your measurements in kilograms since it's an SI unit. Okay. Next thing we need to do is calculate the heat lost by the water. So if you remember the heat change equation for a liquid, or just anything that doesn't change its state, that's going to be MCAT, as some people call it, or MC delta T, where M is of course the mass of whatever you're measuring, C is the specific heat capacity of what you're measuring, and delta T stands for the temperature change. Okay, so we're just going to go ahead and write our formula, because this is physics, and in CSEC physics you do actually get a mark for identifying and writing the correct formula. So even if you don't exactly know how to solve it, just doing this will actually get you a mark. So it's always good to remember to write your formula. So this is the formula we're going to use, MCAT, or MC delta T. The mass of the water is 100 grams. The reason why it's 100 grams is because the 110 grams will actually include the mass of the ice. And we don't want to include the mass of the ice. We just want to know how much heat was lost by the water itself. So that's why we're going to use 100 grams. But to put everything in SI units, instead of using the 4.2 joules per gram per Kelvin, I'm going to convert this to kilograms, right? And all I have to do to convert this to kilograms is to multiply by 1000, because 1000 grams is in 1 kilogram. So if I multiply that by 1000, I'll get 4200 joules per kilogram per Kelvin. So that's what I'm going to be using. So I'm also going to be using this measurement, which is not this exact measurement, sorry. I'm going to be converting this 100 grams to kilograms as well. If you divide 100 by 1000, that's 0.1. That's 0.1 kilograms kg multiplied by 4200 joules per kilogram per Kelvin. and that's going to be, oops, let me not write that, and that's going to be multiplied by the change in temperature. But the reason why I'm not going to change the unit of this is because it's a difference, right? So even if I was to convert these to Kelvin, I would still end up with the same difference. So when I do this calculation, you'll find that this equates to 10, and 0.1 times 10 is of course 1, so it's just going to be 4,200 joules. So that's our heat lost by the water. Okay, next part of the question, we need to write an expression for the total heat gained by the ice in melting and the melted ice in warming to 20 degrees Celsius. Okay, so usually when they highlight this total here, it means that it's not gonna be just one equation. Sometimes it is, but usually it's not. And in this case, it isn't. The reason why it isn't is because the ice is changing its state, right? And then after it changes its state, it's going to warm to 20 degrees Celsius. So we're going to have to apply two different formulae here. One, we're going to have to apply a latent heat formula for the change of state. And we're also going to have to apply a regular heating formula, or a regular energy change formula, which is the MC delta T formula, for the ice warming, or the melted ice rather, warming to 20 degrees Celsius. So to represent total heat gained, I'm just going to write sum, and that's the summation formula. Summation sign. And I'm going to write EH. So this basically means total energy gained to heat, right? And that's going to be equal to MLF. So this is an L. So MLF is the formula for energy due to latent heat, right? So this right here, this LF, is a constant which stands for the latent heat of fusion, specific latent heat of fusion, sorry. And I believe in the next part we're going to need to calculate that. So let's bear this constant in mind. And that's of course plus MC delta T. So this is for the ice warming to 20 degrees after it has been melted. So this formula is for the ice changing to water. So that's the ice at 0 degrees Celsius changing to water at 0 degrees Celsius. And then this formula is for the melted ice at 0 degrees Celsius gaining heat energy and changing to 20 degrees Celsius. Still water, but it's warmer water. So that's your expression. I believe the 2 marks here, there is looking for this formula and this formula. So that should be good. And now they want us to calculate the specific latent heat of fusion of the ice. Okay, so to do this, we're going to need to use an important fact here. So remember that this assumption basically tells us that, as we said earlier, the ice and the water are the only two bodies in this experiment that are exchanging heat, right? So because of that, and because of the law of conservation of energy, which of course states that energy cannot be created nor destroyed, if the water loses energy and the ice gains energy, then all of the energy from the water must go to the ice, right? Because the energy must be conserved. So because of that, we're going to write since EHW, which stands for water, I'm going to say lost. So this is just saying since the energy lost from the water is equal to E sub H I, I'm just going to put gained. And then we can equate this value to this expression. So that's going to be 4,200 joules is equal to MLF plus MC delta T. Okay. So now we can just go ahead and fill in what we know. So we know the mass of the ice, which would be 0.01 kilograms. We also know the specific heat capacity of water, and we know the temperature change. So the only thing we actually don't know is indeed the latent heat of fusion of the ice. But we can solve for it by doing a little bit of algebra. So let's actually just do this over here. Now I'm not going to work with the units when solving for this, because what happens is that when you actually put all of these units, it can be very confusing to transfer, transpose units, divide and multiply, and actually end up with the correct unit. So what I usually like to do is, if I have a big complicated equation like this, then I'd usually just do the algebra, and then at the end I'd make sure that I put it in the correct unit, right? So that's why I like to work with SI units, because if everything's in SI units, then your answer will automatically be in SI units, and CSEC cannot take off any marks. So let's get to it then. So 4,200 is going to be equal to 0.01 times LF plus 0.01, right? Because 0.01 is the mass of the ice, multiplied by 4,200. Since at this stage the ice would be actually melted into water, that's going to be multiplied by 30 minus 20, which is of course a temperature change. Actually, I should put these brackets to be accurate. No, I don't like that. Let's just fix this. Okay. So again, we're using the 0.01 because this is the mass of the ice, right? So we want the energy gained by the ice. We don't want the energy gained by the water again, because that would of course be wrong. Okay, so with a little bit of algebra and some calculations, we're going to get that 4,200 is equal to 0.01 LF plus, let's type this into the calculator, plus 420. And then we're going to say 0.01 LF is equal to 4,200 minus 420, which gives us 3,780. And therefore, I'm going to have to write this here because of space. LF is going to be equal to 3,780 divided by 0.01, which gives us 378, so that's 378,000 actually. And of course, latent heat of fusion is measured in joules per kilogram. It's always important to include your unit in the final answer, just so that CXC knows that you actually know what you're talking about, right? And I believe this does carry a mark as well. Okay, so that's our answer for part D of the question. So now we move on to May-June 2011. So it's from the same year, but in a different month. And they just ask us to complete a table, right? So specific heat capacity has a symbol of C, which we know, and SI unit is joule per kilogram per Kelvin. Okay, and specific latent heat of vaporization has a symbol LV, well L sub V rather, and that has a SI unit of joule per kilogram. Right, some nice easy marks right there, no problem whatsoever. Okay, so now they ask us to define the heat capacity of a substance. Now note carefully, this does not say specific heat capacity of a substance. This says heat capacity. Heat capacity and specific heat capacity actually have two different definitions. There's a very slight change. I'll show you after I write the definition. So we can put the heat capacity of a substance is the amount of energy required to change the let's just expand this, temperature of a substance by 1 unit. You can just put usually 1 Kelvin just to be sure. Okay, so this is the definition for heat capacity of a substance, right? But if this was specific heat capacity, we'd have to factor in the mass, right? So the definition would actually read, the specific heat capacity of a substance is the amount of energy required to change the temperature of 1 unit mass, usually kilograms, of a substance by 1 unit of temperature. Let me add the temperature here. Well, I mean, I don't really have to add that because I actually said change the temperature already. It's implied. Never mind. Okay. So basically the difference between specific heat capacity and regular heat capacity is the mass, really. So that's actually going to come in handy for the next part of this question. I'm actually just going to continue using the text tool here, which asks us to relate the specific heat capacity with the heat capacity. And the equation that does this is capital C is equal to M, stands for mass, times little c. And the reason for that can be seen if we just look at the units. So the unit of big C, which is regular heat capacity, is joules per Kelvin. Sorry, but yes, why did I write kilograms? That's my bad. Yeah, it's joules per Kelvin, right? And the SI unit for little c, which is specific heat capacity, is joules per kilogram per Kelvin. So you can see that if I multiply this by 1 kilogram, which is basically a unit mass, then the kilograms are going to cancel and I'll actually be just left with joule per Kelvin, which is why big C is equal to M times little c. That's a little catchy way to remember it. Big C equals M times little c. That's a way that I hear a lot of people actually remember this, so that's always good to know. But yeah, okay, so I believe that is number 2. So moving on. So a housewife left 25 grams of ice in an open insulated container while she was answering her cell phone. When she returned, the ice at 0 was converted to water at 3 degrees Celsius. Okay. So what is CSEC asking us to do? They're asking us to calculate the energy needed for ice to totally melt and reach its present temperature. Alright. So this kind of gives us a hint of what we're going to have to do. So what I'm going to do is I'm going to start with the ice changing state. So it's going to be melting. And as we remember from the first question, that is going to be equal to M times LF, right? I wrote EH1 because this is our first energy value, right? This is not our total energy, this is just the first one. So that's going to be equal to the mass of the ice, which is 25 grams, so that's 0.25 kilograms. 0.25 multiplied by latent heat of fusion of ice, which is 3 which is 3,000, well, 340,000 actually, and that's in joules per kilogram. Joules per kilogram multiplied by joule is supposed to give us joule. So let's just put this into the calculator. 0.25. Okay, so that's 85,000 joules, of course. It's energy. Okay, so 85,000 joules is our first energy value. Our second energy value is going to be for the ice, which has now melted, so it's now water, changing from 0 degrees Celsius to 3 degrees Celsius. And of course, we're going to be using the good old MC delta T to solve that. So again, that's going to be 0.25 as our mass, multiplied by 4,200, and the temperature change, because of lack of space, I'm not going to write 3 minus 0, because we obviously know that that's 3. So that is our formula. 0.25 multiplied by 4,200 multiplied by 3, that gives us 3,150, and of course that's in joules, because everything there was in SI units except the temperature, but as we explained earlier, it's a temperature difference, so you'd still get 3 either way, even if it's in Celsius or Kelvin. Okay, so now we can go ahead and calculate the total energy needed. So that's going to be represented again by summation EH. And since I should forgot to label this EH2. Okay, so that's going to be equal to EH1 plus EH2, which is of course 85,000 plus 3,150, and let's just type that into the calculator quickly to see what is equal. Okay, so that's 88,150 joules, of course, because that's energy. Again, cannot leave off the units, cannot forget to write the formulae, because those are actually just as important, or in some cases even more important, than our answer, or the value of our answer. Okay, so now they're asking us that if the melting and heat activity took place over 300 seconds, calculate the rate at which the ice was receiving heat. Okay, so we already have the energy, and the rate at which something receives heat is the rate at which it receives energy, and that by definition is actually just power. So we know that power is just energy over time, but in this case I'm going to write E sub h over time just so we can specify exactly what we're talking about, and that's going to be our value of 88,150 divided by 300, and that's supposed to give us to one decimal place 293.8 watts. If you did the units, then it would have been joule per second, but a joule per second is by definition a watt, so that's the SI unit, so that's how we write it. So that's 293.8 watts. Okay, so that's question 3. Question 4 is May, June 2013. So let's look at what they're asking us to do now. So a physicist converts 8 kilograms of water at 33 degrees Celsius to steam at 100 degrees Celsius. Assuming no heat loss, calculate energy required to heat water to 100 degrees Celsius. Okay? So there's no change of state here. This is just our energy change. So we're going to use the MC delta T formula. Right? And that's going to be 8 kilograms, so we don't have to worry about that. And what they give us for the constant, 4,200. Okay, cool. Times 4,200 multiplied by the heat change, which is going to be 100 minus 33. And then we can do the calculations. But before I do the calculations, just a quick side note. It's always good to pay attention to what they give you for these constants here, because these constants may vary in both value and units from question to question. And it's more important to always make sure that you have all your units and values correlated, right? So if, let's say, this was grams and I wanted to use kilograms here, I couldn't use the one that they gave me in grams. I'd have to convert it to kilograms, right? So that's an example for the units. But otherwise, if the values are different, then the value that you're used to, which would probably be 4,200, let's say they gave you, I don't know, 4,196. That's not an accurate value. It's just a hypothetical situation. And if you use the 4,200 and your answer is wrong, then they have the power to take off a mark because of that, because they actually gave you the constant. So it's always good to make sure that the value is the one that they gave you and that your units are all matching, so that you don't make any mistakes and throw away free marks. Okay, so with that side note done, let's just go ahead and get this calculation out of the way. So let's just type all of this into a calculator, and that gives us a pretty large number, which is I believe 2,251,200. So yeah, that's a pretty big number. This right here, and of course that's in joules. The energy required to convert the water to steam at 100 degrees Celsius. Okay, so that's gonna be again E sub H, but this time we're gonna be using the MLV formula, which is of course the latent heat of vaporization, well, the energy from latent heat of vaporization for water. And we're gonna have to be using this really large number over here. That's gonna be 8 multiplied by 2, basically 2.3 million. So that's a lot. It's a lot of energy. Put this into a calculator. We get an even bigger number, which I believe is actually 18,400,000. So let's just go ahead, 400,000 I should say. Let's just go ahead and write that. And then they're asking for the total energy in megajoules required to heat this 8 kilograms of water at 33 degrees Celsius to steam at 100 degrees Celsius. So for this, we're just gonna add our values that we calculated earlier, but we're gonna have to do some conversions, right? Because we're in joules at the moment and they want it in megajoules. So let's just write down the addition and do it quickly. 2,251,200 plus 184 and a lot of zeros. Okay, just put a bracket around that, says joules. Okay, so that's 18,400,000 plus 2,251,000 which gives us 20,651,000. Yep. Okay. And that's in joules, but I wanted in megajoules, so let's just quickly convert that. So to convert from joules to megajoules, you have to remember that a megajoule is actually 1 million joules. So that's 10 to the 6, if you actually remember it better that way. So to do that, we actually just have to divide by a million now. So let's just go ahead and do that. Divide this by a million, and you get 20.651. So let's just write that as 20.65. That's megajoules. Mega is the capital M, milli is the common M, so that's important to remember that difference. And that is indeed our answer. Okay. So now let's see what number 5 is saying. So number 5 is, we're dealing with another physicist. So this time he's converting 2 kilograms of water at 37 degrees Celsius to steam at 100 degrees Celsius. Okay, so this physicist is doing something pretty similar to what this physicist did. And this is a good sign, because that means that CSEC likes to repeat certain questions, not with the exact same values, but with the same concept. So by watching this video and by doing these questions, let's hope that whenever you do CSEC, you'll get a question pretty similar. So I don't believe that we actually need to work out this question, since we know exactly how to do it. Right, but what I will do is I will work it out on the calculator, and I'll put the answers there if you just wanted to check. So to heat the water at 100 degrees Celsius, let's just write a big EH, we're just going to write the answer here. Again, we're going to go 2 kilograms. We're going to be using MC delta T, of course, because the water has not changed state yet. So it's 2 kilograms of water times 4,200, which is our specific heat capacity, given down here. Right, and that's going to be multiplied by the temperature change, which is 100 minus 37. And so that gives us 529,000. 529,200. So that's our first value. Right, and then to heat the water from 100 C to steam at 100 C. So again, this is a state change. So what that's going to require is our MLV. Oh, actually, I'm just going to write the formula as well, come to think of it, just so we all know what formula to use, but I won't be doing the actual algebra and actual arithmetic to work these out. Okay, so that's going to give us again same mass, but times the latent heat of vaporization constant down here, which they gave us as 2.3 million this time. Right, same as what they gave us up here. So that's going to be 2 times 2.3 million, which is, of course, 4.6 million. So you could write this as 4.6 times 10 to the 6, which is in standard form. So that's also an option. So this is one way to write it. This is another way to write it. Either way, I believe works, so it's up to you. Right, and then to completely convert the water to steam, it's going to be the sum, and we're going to, of course, add these two values again. So that's going to be 529,200 plus 4,600,000, and that gives us 5,129,200. And this is of course in joules because it's energy. Okay, so that is question 5 complete. These are the answers that I've gotten. So if you wanted to check these values for yourself, then here they are. Okay, so it actually happens at number 6 right here. Number 6 is actually the exact same question as number 1. So we're actually not going to do this question entirely because we've already covered that. It's right up here. If you'd like to see answers for that and how we did that question, you can rewind the video to number 1. But otherwise, let's move on to number 7. Okay, so what does number 7 say? Number 7 is asking us to, I believe, calculate the specific latent heat of vaporization of water. Okay, so what they gave us some data in an experiment using a heater to obtain the latent heat of vaporization of water. So they gave us a mass of a can and water, gave us the mass of the can and water at the end of the boiling and at the beginning, the power of the heater, and the time of heating. Okay, so how are we going to do this? At the point of watching this video, I'm not sure if you have done an experiment to do this, but if you have done an experiment to do this, then you'll probably know how we're supposed to do this, right? So the way how we're going to do this is by first determining the mass of water that has changed to gas. And the reason why we know it's changed to gas is because at the start we had 0.28 kilograms, and when we finished it was 0.26, right? So if we lost some of that water, then the only logical place that water could have gone is that it vaporized and dispersed into the air, right? So that means that 0.02 kilograms of water was vaporized, right? So now we have a mass of water that was vaporized, and we can actually use that to calculate the specific latent heat of vaporization of the water. How are we going to do that? We're going to do that by using these two values right here, which is the power and the time. Because if you remember, power times time is energy. And based on the conservation of energy, if we are assuming negligible heat loss, then the power from the heater must have fully supplied the energy for the water to change state, right? So then we can go ahead and write this equation right here, which is power times time is equal to m LV. So what this is saying is that the energy that was supplied by the heater is the energy that the water used to vaporize, right? So we can use this to calculate the constant, which is specific latent heat of vaporization. Okay, so without further ado, let's get to it. So the first thing we need to do is just write what the mass is. So the mass is just going to be 0.28 minus 0.26. That's of course in kilograms. And that is equal to 0.02 kilograms, right? And then we can go ahead and fill in some values. Oh, actually, before we do that, let's convert this time to seconds. So just so that we know, so 5 minutes is actually going to be 5 times 60 seconds, right? Because 1 minute is 60 seconds. So that's actually just 300 seconds, right? So you can go ahead and fill in the values now. So that's our power times our time, 150 times 300, and that's equal to 0.02 times LV. And then 150 times 300 is 45,000. So 45,000 is equal to 0.02 multiplied by LV. So you can just divide out the 0.02, and 45,000 divided by 0.02 gives us 2,250,000. And if you realize, that's actually pretty close to the constant for a specific latent heat of vaporization that they gave us earlier. So that's a good indication that we've done the right thing. See, they gave us 2.3 mil, we got 2.25 mil. So pretty close. Right, and that is, I believe, the end of our worksheet and the end of our questions for today. So, as per usual, I hope that you've picked up something useful, whether you've learned something, whether it was just review, anything at all. Hope that you got something good from this video, and I want to thank you for watching, and I will hopefully see you in another video. But goodbye for now.